In this video, I'll be explaining SuMaEM, which is an extension of SuMa++ using Expectation-Maximization. The first thing we need to understand is SLAM. SLAM stands for Simultaneous Localization and Mapping. Localization gives us the robot's location, and mapping gives us the robot's view of the environment and maintains a map of what it's seen already. Knowing where the robot is and what it sees is essential for higher-level tasks, such as planning. SuMa++ achieves SLAM using something called circles. These are a basic element of some graphics engines. SuMa++ uses a variant known as Semantic SLAM. This means it uses semantic information to determine what objects are rather than only where they are. For example, the Pac-Man on the left knows where things are but not what they are. Semantic SLAM provides the context required to produce a more meaningful map. We extend SuMa++ to better utilize its semantic information. There are a few different methods we developed. The first is Kerentropy. The second one is a heuristic based on meta-semantics. And the final one is integrating Semantic ICP into SuMa++. Each of our extensions modifies the cost function. First, we'll look at the original cost function for SuMa++. For each of the methods, you'll see some modification to the weight, here denoted by W sub I. Diving into the first idea, which uses Kerentropy, we can see that any two random variables, x and y, which are very different, have a low Kerentropy. However, if x is equal to y, the maximum Kerentropy is achieved. Therefore, we can use Kerentropy to determine how similar two variables are. We then take the derivative and maximize the Kerentropy, which is the same as minimizing the error. We use this because it's highly resistant to noise. You can see in the cost function for Kerentropy, we've modified W sub I to be multiplied by G sub I k. The second idea we developed is a heuristic based on the semantic information. Points which are static, such as buildings or fences, should be much less likely to change between frames. We use this assumption when we develop a new weighting scheme. This new scheme allows us to be more certain about the location of static objects, and can be combined with the first idea from Kerentropy for even better performance. You can compare the original weight, W sub I, with W sub I new, our new weight, to see what we've changed. Next, you can look at the cost function and see that we've integrated in W sub I new as well as G sub I k to combine both ideas, Kerentropy and our heuristic. Finally, we have the integration of Semantic ICP using the confusion matrix. This method was developed by using Semantic ICP, which is a semantic inference method. We replace the expectation weight in SuMa++ with the expectation of Semantic ICP. After implementing all these methods and drawing extensively on the SuMa++ source code, we tested on the Kitty dataset. Our tests show that we were able to perform SLAM very effectively. On some datasets, we outperform SuMa++, but on others we perform near or even slightly below. Though it fails to achieve full supremacy over SuMa++, we show it's very effective for datasets with smooth initial paths, and datasets with rapid change in the beginning of a path cause our method to perform near the level of SuMa++, but slightly worse. All of our code can be found in our GitHub in our description. Everything is open source, and we invite anyone to use, build, or extend our method without any restriction. With better SLAM algorithms, robots can be much more effective in applications such as disaster relief and marine or space exploration. We hope our contributions can be used to allow robotics to more effectively assist humanity in all our endeavors.